I'm Kia Kokalitcheva. I'm a reporter with Axios. I cover tech and venture capital out here in the Valley. And I'm here with Eric Schmidt, who is a former CEO and chairman of Google. And he's also doing a whole lot of other things and spending some of his time on quantum computing. So we're going to be chatting about that today. Welcome, Eric.
Thank you very much, Kia.
So we're just going to jump right into it. Tell me, why are you spending your time on quantum computing? Why should we care about it?
Well, it's funny that I'm old enough that you see life and circumstances return. When I started programming, I was programming in an IBM Assembler 360 language, and it feels like quantum computing is exactly at that point. We don't have any of the layers above. We don't have common platforms. We don't have common languages. We don't have a way of taking a compiler that will take some programming language and then sorting it out to whichever architecture. We know this stuff's going to happen 5 to 8 years from now. So now is the time to be getting those platforms built and get ready for them. It's going to be incredible when it happens.
And so, why is this a technology that you're spending your time on? You could be doing so many other things every day. So, why is this a particular technology that you think requires attention now?
Well, a lot of people have been watching the progress of Moore's Law, and we're now at 5 nanometers, 3 nanometers. There will be further improvements in architecture. But at some point, Moore's Law will really finally begin to degrade. It already has to some degree. So here comes along a form of computing that makes no sense to a normal person, that somehow is able to do this specialized calculations instantaneously. And we now have languages that will allow you to program in it. We have an algorithm called Shor's algorithm, which is known to actually work for prime factoring and those sorts of things. And we know that these systems will be useful for essentially optimization problems. What's interesting to me is having moved last generation from lecture to CMOS and so forth, this one starts cloud native. So you can imagine that in the next few years, there will be these, I'm going to call them QPUs for lack of a better word, that will be associated with a cloud service provider who will also have TPUs and GPUs and traditional processing units. And somehow the system's going to figure out which algorithm goes where. Initially, very poorly, but eventually these systems will be so smart, they'll figure out how to optimally solve your problem. And that's the power of computer science.
hmm So that actually brings up my next question, which is about timelines. I know in the last year or two, we've been getting a lot of announcement from various companies, some big like Google and IBM, some smaller ones about milestones that they've reached. What is a timeline that you kind of foresee in terms of this technology doing anything useful, for lack of a better term?
So they're on the order of 5 different approaches around the world, all of which have required enormous amounts of investment. Again, not unlike the 50s and 60s and so forth. And they're producing almost accurate computers. They're called NIST computers. They're sort of not quite accurate and they have errors. And the important thing is that if you add enough of the not so accurate computers, you can, using various techniques, get really accurate computers. One estimate is that if you want 1,000 qubits, you need 1,000,000 actual current qubits, if you will. So we're all in this phase where we've just shown quantum supremacy. The other approaches are showing promise in very small number of error probability based qubits, 50, 60, 70. And we need to go from 50, 60, 70 to 100,000 to 1,000,000. And that's largely an industrial problem. All the techniques have different approaches. There's one which is essentially can use existing CMOS technologies, which will be very cost effective. Others require this enormous freezer technology to get now down to basically 0 degrees Kelvin, which is impressive in and of itself. But all of them have the property that there's not enough of them to provide a coherent and accurate and stable long-term answer. What you want is you want the computer to work all the time. You want it to produce the same actor all the time. You don't want it to have blue screens, if you will. And you want the state to be held for a while. And that's mostly engineering at this point. It's powerful engineering, but you can see that it's going to happen. Most people I've talked with believe it's within a decade. It's not 20 years.
Okay.
And this is really important because when this thing shows up, it has a lot of implications. The most obvious one being in terms of the ability to decrypt that were thought to be undecryptable. But there are many other things that will be possible. But I want to go back to when we can solve core problems in material science, core problems in energy, batteries and solar and so forth, quantum chemistry, though it will produce this explosion of applications, not unlike what I saw in the 1980s and 1990s. It's the same thing,
Hmm.
right? The vastly more powerful computer.
Hmm. So you're thinking a decade roughly is when we can really start to bridge into truly applying this to problems.
And I think the sequence goes like this. First, it's clearly cloud native, so that's good. You don't have to rebuild all of that. The second thing is you've got to figure out a way to build replicable and larger systems, and you have to figure out programming languages. Google has offered one
Hmm.
to the open source community called Circ. It's fine. If that one doesn't prevail, something else will prevail. But eventually, what's going to happen? And I'm not kidding you. People will be writing in the equivalent of Python and PyTorch again 8, 9, 10 years from now, and it'll be handled automatically. When that happens, it's a revolution because most people are having trouble understanding how to program these very specialized devices in terms of the way quantum works, and developing compilers that can actually understand that and take the programmer's intent in the traditional way that we all program and turn it into an outcome will be revolutionary. And all of those are under development now.
Hmm. Um, since you mentioned earlier the 50s and the huge government sort of investment in the technologies of the time, where do you think a lot of the quantum and even AI, broadly speaking, where do you think a lot of the best tech advancements are going to come out of? The private sector, things that the government's research they're funding, academia, and what relationship do you think those different arenas are going to have in pushing this technology forward?
So China is interesting because China, a number of the researchers that worked on some of the early quantum work in the United States moved to China, and under the guidance of President Xi, they've put together a national quantum program, which started off focusing
Mhm.
on essentially photonics, and is now basically focused on communications, quantum communications, the ability to have secret conversations and things like that. They're clearly ahead in some of those areas. Their commitment publicly is $10 billion. I have no idea how accurate these numbers are. Often the numbers from China are not correct, but we do know that they're doing. The United States model is different. It has always been true since Vannevar Bush in 1945 that the government does early stage funding and gains occur in private sector, and you're seeing that here, that the gains that we're seeing are profoundly occurring because of large private companies or public companies, if you will, that see a long-term business interest in it. And this is sort of how our system works. It's not bad. The companies move more quickly than the government, especially in the United States. And the Trump administration, one of the things that they did well is they announced a national quantum initiative to try to focus funding and focus research. And I'm sure that that will continue and be grown significantly under the Biden administration.
Hmm. So you're thinking that a lot of funding should come from the government for scale, but you're expecting the private sector will.
Actually, not. In the United States, the government is going to continue to provide very early stage research in this area. But as per the norm in America, the majority of the funding, in terms of especially the commercialization of this, will be done by
Mhm.
essentially public American corporations, IBM,
Okay.
Google, Facebook, Microsoft, so forth. There are a number of interesting startups in this area that will raise, again, private funding. And again, this stage is expensive because the hardware is expensive. There's a lot of risk. It's appropriate for this private public partnership in the United States to work the way it does.
Hmm. Hmm. Um, Shifting gears a little bit, but I've read some recent comments from yours. I think in Time Magazine, where you talked about your concern around all these technologies is that they'll be widely available at some point, which means that bad actors will get their hands on them and do things we may not want in the world, to have this technology applied to. Given what we just talked about with private company or the private sector developing quantum and all kinds of other things, and the government also getting involved, how do you can we trust the companies to do the right thing with these technologies that are so powerful or will be? Can we trust the government to do that? How do you think about that?
Um, every new technology that's really powerful is dual use. I'll give you an example in terms of quantum sensing. A reasonable expectation is that magnetometry as we know it will disappear. It turns out that these quantum systems over the next decade will be far more sensitive to magnetic changes. And a good example there is that that's how your heart will be checked. That's how other aspects of human bodies will be checked. It's also how things that are going on in the natural world will be followed, because trivial, tiny little magnetic changes will do things. Obviously, a dual use technology as well. So it's appropriate to ask the question that you asked, and it's probably early now to say what's an appropriate use and what's a not appropriate use. It has been assumed for 10 years that the ability to break prime factorization, which is at the core of RSA, will allow this basically store now and decrypt later, which is what people are doing to enable it. My guess is that's going to happen regardless of what we do. So I strongly would say to our audience that now is the time to change your encryption from the RSA standards from 30 years ago, and they did well for us, to new emerging NIST standards that are quantum essentially resistant. As far as we can tell, these new solutions, which are available now, are not breakable by quantum mechanisms. The reason you should act now, for example, is because we know that foreign powers, and I won't go into the details, are busy recording everything. And it is their plan 10 years from now, to decrypt everything. And so I'd rather get the stuff encrypted now, stop the current leakage, if you will, of future encrypted data. I'd like to get it fixed now. A number of companies are now working on how to combine RSA and these more powerful tools. It's right at the edge, and I strongly encourage the audience to take this seriously. You have time now, you don't have time in the future. So get your act together around this. I'm sorry to be so blunt, but security matters a lot on these always on networks. And here's something that you can do now to prepare for a very likely future in maybe 10 plus years.
I mean, that's kind of the point, right? Like you're talking about and worrying about these things that other foreign powers could do to us and to whoever they deem their enemies. So how do we think about preventing ourselves, our companies, people in the U.S. who may have access from becoming those bad actors? Obviously, in the last 4 years, we've seen there's a lot of disagreement around what's good, what's bad, what should companies do. Google has been in hot water for its decisions of doing certain things with tech. How do you think about that? Who should be developing these sort of parameters or frameworks? Because as you said, now is the time to think about it.
So if you go back to the way recombinant DNA was ultimately treated, there were a series of meetings, most famously an Asilomar meeting, where the really, really smart technical people who also had a sort of public interest got together, and they formulated a set of guidelines which have withstood sounds like 35 years of pressure and poking from different things about the use of technology. There was recently a similar meeting about 2 years ago on the consensus around the use of human embryos and experimentation on humans using the newest techniques in genetics. And the conclusion, of course, was not to, and that's been enforced again by policy. I would suggest that as we get closer to the scenario you're describing, which I think will occur, there will be similar meetings where a consensus will emerge as to what should be kept very safe and what should be allowed out. There are plenty of laws on the books that cover this. There's a law called CFIUS, which governs much of this technology. But I can assure you that because people are aware of the power of this technology, there will be some kind of intervention of that sort. I don't think it's necessary now because it's too early, but I think you're right that it will
Sure.
be.
So, for the entrepreneurs or researchers in our audience who are, you know, committing or already have been spending a lot of their years, professional years on this tech, what would you say they should be doing today in terms of thinking about this kind of ethical stuff? Or, as you said, is that just not really on the menu right now at all?
Um, well, first place, I always think the tech people should understand the dual use nature of their technology, and they should think a lot about the nature of the technology that they're building and the possible misuse. You could imagine that this technology would eventually, this is a long, long time from now, be sufficiently widely spread that bad actors who are not well funded and not under government control could misuse it. I think it's going to be a long time for that, but you can imagine that. I
Mhm.
want people to think about it, and I want people to think about it now. I would also say, by the way, that these technologies always seem like they're around the corner, but people have been working on quantum in one form or another for more than 30 years. We're probably less than a
Mhm.
decade away, but we're more than 1 year away. Um, it just takes a long time. The innovation cycle for fundamental new technologies is at least 30 years, and we're in the middle of that. So let's
Mhm.
understand that we're going to be at this for a long time. We have to get the details right. I do think that we should start to prepare for the software explosion that I was describing. If I had
Yeah.
understood that when the integrated circuit was invented in 1959, I think, and the Intel 4004 came out in roughly 1970, if I had understood the software revolution that would have occurred as a result of the integrated circuit, right? If I had been able to see the next 20 years, I would have been able to compress so much time, right? By getting those ideas built, the initial teams built, and so forth. Now, this created the companies that are the most valuable companies in America and in China. So the sort
Mhm.
of companies that I'm describing is somewhere around $8 trillion. Now, it took 40 years. So the scale of these fundamental advancements allows for huge long-term market effects if you stay with it. So if you can imagine fundamental tools to help you discover drugs, to understand chemistry, to produce better materials, right, to redo energy systems to make them far more efficient, what's the economic value of those companies? It's very high, right? So it's time now to get started on those with this notion that this will come. It's clearly going to happen, and we just need to wait for it.
Mhm. Um, there's been some chatter recently that you might be getting tapped by the Biden administration to have a role over there. Obviously, I'm sure early conversations, but is quantum technology and other advanced tech something you would want to make sure that this administration is taking seriously and taking the right steps? And even if you're not part of it, what would you want to see the US government do now?
So let me not talk about the Biden administration, except to say that I'm a big supporter of Biden. I think it's been well known. I worked on his campaign and tried to assist in his election, and I could not be happier. The Biden administration will clearly put science back where it's correctly sitting, which is it's called true. And we're going to stop these stupid debates. I mean, I wish I could wish away cancer and things like this, but the fact of the matter is science still rules. I wish it didn't sometimes. So the Biden administration will clearly prioritize American competitiveness. The thing I'm working on, and my friends who are likely to be in the Biden administration, and to the degree I can assist them, all of us want America to be as competitive in the future as it has in the last 50 years, which is why I've been so successful. It's not because I worked so hard, it's because I was lucky, because I had all of these people building this platform below me that really, really created this and allowed me an opportunity as an individual contributor to move things forward. I want the same thing to happen in America for the next 50 years. The way you do that, sorry to get on the soapbox, but you start by saying that the government is an essential part of the early funding. I was initially on an NSF and essentially ARPA funds because I couldn't afford it anywhere else. I owe my career and my success to the federal government way back when. I want the same person today to get that same support. We've called in a commission that I run called the AI Commission. We've called for a doubling of funding in these areas. I think that that is the minimum that we should do. We've also called
Mhm.
for high skills immigration, working with our technology partners and alliances, and quite a few other technical changes. I'm quite sure that the Biden administration will science to where it should be, and I'm quite sure the Biden administration will actively promote increases in funding and collaboration with our partners. It's time and it's late, and Trump should have done this too.
Super quickly, what kind of amount do you think we should be spending every year?
Well, I'll tell you the numbers are quite disturbing. Our R&D spending as a country are down below 0.7%, which is below the number that we were spending as a percentage of GDP for Sputnik. So we've gotten lazy. We have lost our claim to being the only innovator. We're letting these other countries innovate, including China, but others. How is that okay? The investment, this relatively small amount of investment from the federal government and the states as well, has created the GPS. If you like fracking, it created fracking. If you like self-driving cars, it created self-driving cars. It created every aspect of the technical industry, which now drives, I think, roughly 1/5 of our stock market in the United States, which is doing really well, is driven by doing really well tech companies. So you want to know where that money went? It went ultimately to the shareholders and the citizens of our country. I want that cycle repeated.
Got it. Well, thank you so much for taking the time. This was a great conversation.
And thank you. And this is a fantastic conference. I'm so glad you guys are doing it.